The following is a keynote speaker presentation from the ACM 97 conference, The Next 50 Years of Computing. ACM 97 brought together over 2,000 leaders and luminaries from all aspects of the computing world to discuss and predict what the next 50 years of computing has in store. ACM 97 underwriters were Computerworld, Hewlett Packard, Intel, Microsoft, and Sun Microsystems. Sponsors were Cadmus Journal Services, IBM, Netscape, Popular Science, Sheridan Printing Company Incorporated, Silicon Graphics Incorporated, SoftBank, and Unisys. The event also included a major exposition with a paleotechnic look back to the future from the year 2047, and a specially commissioned book, Beyond Calculation, featuring essays on the next 50 years of computing by luminaries and pioneers in the field. The ACM 97 conference was chaired by Robert Metcalf and emceed by James Burke. Details on how to obtain more information on ACM 97 follow this program.
Ladies and gentlemen, James Burke.
Our next speaker is one of the industry's greatest teachers. So when he finishes, there will be a test. He's the Moore Professor of Engineering and Applied Science at Caltech, where he's been since he got his PhD there in 1960. Now, he's a member of so many associations. I'll just mention a couple. The IEEE, the National Academy of Engineering, the National Academy of Sciences, the Royal Swedish Academy of Engineering Sciences, the American Academy of Arts and Sciences, and the Franklin Institute. And his very many awards include the IEEE Centennial Medal for Extraordinary Achievement, as well as its von Neumann Medal for, quote, leadership and innovative contributions to VLSI and creative microelectronic structures. You'll gather from that he has something to do with VLSI. In fact, he pioneered the field. Today at Caltech, he focuses on modeling neuronal structures, and his latest book is entitled Analog VLSI and Neural Systems. So I suppose you could say he does a great deal of thinking about thinking. That's an English joke. I won't do another one. I have no doubt, however, that its thinking is what you will be doing after you hear what he has to say, because he's going to speak about the future of semiconductors, and that subject so close to everybody's forecast charts, how long will Moore's law persist? A matter that may have some bearing on what you or your company may be up to, or not up to, in the relatively near future. Please join me in welcoming Carver Mead.
I want to start by reminding you of things that you all already know, many of you much better than I do. Computation started with a belief, basically, a conjecture that any computation could be done by this funny thing we call a Turing machine. It's really just a model of computation, a thing that got made up in a person's head. It was actually a model of mathematicians proving theorems. So that's an interesting thing. I have a little different view of computable functions. I think computable functions really are the things that you can sit down and run on your PC or workstation or whatever. Now, I'm not the first person to think this. Of course, that's an old idea, and there's a whole science of complexity theory which deals with all that. And it's interesting when you look at it. What do we believe about computing? Well, at least from a scientific point of view, we use the word time to mean how many steps it takes on our computer to do something. By space, we don't mean space in the physicist sense. We mean how much memory does it take to do this problem. And the assumption underneath all that really is that all computers are basically alike within some small factor. And once we've defined computers to be all alike except for the year in which they were made, we can define a set of problems that are tractable, namely the ones we can run on our PC and it gets done before dinner. And the intractable ones, the ones that we run over the weekend and it still seems to be running, but we're not sure. We've all done things like that. Those problems are characterized by a very large number of alternatives, exponential in the worst case, and not any really good way to make shortcuts. And so the poor little thing sits there and just struggles away with all that. And this conference really is about congratulating ourselves on how we're changing the world and all that. But I would like to call attention to the fact that there are an interesting class of problems that we're not doing so well on. And that's why it's kind of interesting at a conference like this to talk about them. Most interesting optimization problems are like that. But what's really interesting is that all the perception problems are like that. Hearing, vision, any of those things. Now, that wouldn't be so bad if, none of us can do them on computer to first order. You saw in Gordon's talk that the failed predictions about any of the perception problems kept failing and kept failing and kept failing and are still failing as we speak. It wouldn't be so embarrassing if it weren't for the fact that all, even very dumb animals like the fly, do them very, very well. And that's embarrassing. That's really embarrassing. Well, from a point of view of us as people building computers, what if we could make a different kind of machine? What if we could make a machine where the capability, the computational capability, got bigger exponentially with the size of the machine instead of linearly or slightly sublinearly like it does today? That would be an interesting thing. That would be different. That would change the game, because no longer would we be stuck in this thing where we keep making these predictions. We're going to do speech recognition, or we're going to do artificial vision, or we're going to do these sort of artificial intelligence kinds of things. And it keeps not happening, and it keeps not happening because these problems are exponential. Or my colleagues always caution me and say, well, many of these problems aren't really provably exponential. They may be just a very high power. Well, okay, very high power. That's all right. Well, this talk is sort of a personal confession of mine for my last 30 years of work. Could somewhere there be hiding a form of machine that would do something like this? Because that would be interesting. That wouldn't be just building one more machine. And there are some candidate structures. Ultra-parallel VLSI would be interesting and might do something like that. Neural computing structures, we know, do something like that because we use them to watch each other and do that sort of thing, listen to each other. And then there's a bunch of furor right now about quantum computing structures, and I'll say a couple of words about that toward the end. Well, I worked a long time on ultra-parallel VLSI structures, and as in so many things, there's some good news and some bad news. The good news is that we've finally learned how to design this stuff to where it sometimes works on first silicon, and it usually works on second silicon. And they do some things very, very well, and that's all very nice. But the bad news is that the speedup is polynomial at best, and usually linear in the amount of stuff that you put there. So what's going on? Well, let me once again insult everyone's intelligence and remind you about digital systems, because I I think nowhere in the literature on this conference was it said we were talking about digital systems, but I think most people here assume that that's what we're talking about. What is a digital system after all, and why is it a good idea? Well, you all know what they are, but let it be said one more time. Digital systems represent information by a finite set of discrete symbols. That's not a new idea. It came from the invention of the alphabet, as you said, some 1,500 years BC. And so it's not a new idea. So why is it such a big deal now? Why did it take so long? Well, it's a good idea for a very simple reason. Let me give the sort of simplest, most brain-dead example. If we have some information that starts out with a 1 or a 0, that's the simplest one that I know. And now that physical information, that's another thing that doesn't get said too much, that in cyberspace it's somehow kind of hard to remember that there's a physics of stuff out there. Like the information has to get stored somewhere, it has to get transmitted through something, it has to be received by something, and so forth. That's all physical stuff. And that physical stuff has its own properties, which tends to take a nice sharp distributions of 1s and 0s and turn it into a distribution here, which is a little broader. Now, if you keep doing that step after step after step, the distributions go broader and broader and finally overlap, and finally you lose the information. But never mind. What we do is we put the whole thing through a contractive mapping, which is illustrated here by this transfer curve for a logic element, and it comes out the other side as good as new. So that's the big deal about digital. And oh, by the way, there are a lot of more complex examples like error correcting codes and all, but they all rely on this discreteness of the underlying symbols to do that. Well, with that art form, we congratulate ourselves on being able to do things so that we can reconstruct them perfectly, and rightly so. But the form itself carries with it some limitations. Well, if one is looking at doing something beyond the limitations, maybe one ought to look at what the limitations are. So what we mean by time, remember, was the number of steps of some machine going along. It didn't really have much to do with time. In fact, these machines don't really have a representation for time per se in any natural way. The continuous variables, of course, have to be represented by numbers, strings of these discrete symbols. And they have to get processed in discrete chunks, one at a time. So there's no notion of locality or continuity that we have in the physical world. And much of what goes on in the physical world is really simplified a great deal by the continuity that exists there, and that continuity is lost when we've digitized the information. So all the alternative hypotheses for the solution to one of these exponential problems have to be spelled out in these discrete symbols without any natural continuity between them, and for that reason we just go and work them one at a time, one after another. And it comes back to the fact that the power of the digital system is also its Achilles heel. The fact that we quantize after every very simple computation means that we lose that very important continuity, which is a representation of physics. It's the nature of the world out there. And we've lost it when we did our digital. Well, as I said, it wouldn't be at all embarrassing, except there are systems which handle this kind of problem and handle it very nicely. This is an illustration out of Ramon Quijal's original book on the histology of the nervous system, and it just shows a few of the typical kinds of nerve cells in the brain. This is a structure which solves the kind of problems that we have broken our pick on down through the last 50 years without really having made a dent in it. If you look at one of these computing elements, it's rather strikingly different from our standard digital computer. It's made out of goo, and that's not quite so striking, but what is striking is that it has of the order of 10,000 inputs instead of the 2.5 plus or minus 1 or 2 that our standard logic gates do. And this is the input stuff up here, and the output comes out down below. And you'll notice that these little bumpies, they're called spines, that exist on the input side of the neuron. Those are where the inputs come in, and the inputs are clustered sort of rather far from where the quantization gets done down here in the body of the cell. Well, what happens here that does all this marvelous computation? Well, the inputs come in as pulses. They're discrete in time and discrete in amplitude, but the time of arrival, the relative time of arrival among the nerve pulses coming in is distributed. It's a continuous variable, and that's where the information is encoded. Certain combinations of nerve pulses arrive up here in the distant parts of the neuron, and they propagate down through these active processes. There's a distributed amplification that goes on there, which has to be done just right. If you turn up the gain a little too much, those little signals that are coming down grow up and become just another nerve pulse, and they quantize too soon. If the gain isn't enough, the little signals are coming down and they get lost on the way, so the thing has to be tuned up just right. We still don't know how to do that with artificial circuits, but we're working on it, and it looks like a doable thing. What happens in a structure like this, we think, and it isn't known with great certainty at this point, is that act of keeping all the little signals that come in various places at various times and propagate down with just the right velocity, so when they come together at these junctions, they come together with some sort of nonlinear interaction. That is actually a structure that keeps alive an exponential number of possibilities, all in the same structure at the same time. And that's exciting. That means this may in fact be a structure whose computational capability goes exponentially with its size. Yeah, this may in fact be the structure that does it, which is why I've spent the last 15 years of my life trying to understand these things and trying to build little models of things that do something like that, because after all, electronics, the physics of electronics and the physics of the nervous system, even though it's goo, it's electrical goo after all, and has electrical signals in it, and we can make electrical signals too in silicon, and it has all the same continuity properties and gain possibilities that exist in the nervous tissue. And we've managed to build some things. Gordon mentioned that it would be nice to have an existence proof, that you could do something that was even remotely related to the thing you set out to do. Well, we've done some things that are remotely related to what we set out to do. It turned out to be much harder than we thought to do anything that even remotely looks like the nervous system. We've built some retinas, we've built some things that look for motion and stereo and that sort of thing. We've built some cochleas and some things that might be really good cochlear implants. We've built some systems that allow the whole thing to learn as it goes along. And I mentioned that the thing had to tune itself up, or otherwise it was going to either go wildly unstable and you have massive epilepsy, and that's not good. Or the signals all die out and you become why, right? So then that wouldn't be good either. And one can now do learning that's distributed throughout the system and works in continuous time, and that's all very nice. And one can imagine a system that is one level of a nervous system. It might look something like this, conceptually. It has an input. That input comes in real time. And you have some kind of model, that is some kind of network of these artificial neurons. And the job of the network of artificial neurons is to predict what the input's going to do next. There's some obvious evolutionary advantages in being able to predict what happens next, not just for companies, but for individuals as well. Then the output comes out here and goes up, and by that time, the thing that actually happened rolls around, and you can look at both of them and say, did I make the right comparison? Did I make the right prediction? Just like Gordon just did, except you're doing this on a millisecond by millisecond basis. If you've made the wrong prediction, you do two things. You correct the model a little bit, and you send the output out to the next level of the nervous system. It's well known that the way the nervous system works, it only brings things to your attention that are interesting and aren't just routine stuff. So the nervous system's interested in things it's not predicting rather than in the things that are all old hat. It's a little like attendees at conferences that way. You know. I think when one has this kind of system, we don't have this yet, but we're close. Close means probably another 10 years. We'll be able to build systems that sit and look at the world in real time and extract from it what the interesting information is and filter that through several levels of that until the stuff that comes to the attention up at the top is the interesting stuff, interesting in the same sense that you and I mean interesting when we see things. So that's one possibility for a computing paradigm that's very, very different than anything we know today. And has the possibility of directly addressing some of these hard problems that we really haven't touched. The other possibility is to use a quantum system, and there's a lot of noise about this today. In fact, in your very own hometown, there's been a lot of noise generated. And so I should say just a few words about this. The title says quantum computation. What does it mean? Well, what it means is you take some quantum system where the phase of the wave function of the electrons is preserved. You can do this with a bunch of atoms, or you can do it in a superconductor, or you can do it in a lot of different ways. And no one, by the way, has a way that really works in any real computational sense yet. But one could imagine that that could come along if we got the ideas right. And you encode the information in the wave function of the electrons. Now, if you do that for one electron, it's not very interesting. It just kind of goes around and does the same thing. But if you encode it in the wave function for many electrons, each electron can be described, the wave function for it can be described in some kind of space. And the coupled wave function of many electrons is in a space which is the Cartesian product of the spaces for the original one. So you enormously enlarge the space within which this collective system is evolving. Well, that sounds like an exponential to me, so that's interesting. Then you watch this time evolution. Of course, you have to be careful with quantum systems, because if you watch them too much, they get nervous and do something stupid. But if you're careful about all that, you can, in principle, you can get computations done that are of this exponential character. And the most famous one, we heard a little about encryption last night. The most famous one that has been done to date is to show that the factoring of large numbers, upon which many of the public key encryption systems rest, is actually a very easy problem if you do it with a system like this. And it can be done in a very short time, even for very long numbers, in principle. No one has built a quantum system which actually does this now, and there are lots of problems in doing that. But I sort of think, along with Gordon, if you can see a principle that's based in physical reality, at some point we're going to find a way to embody that in a physical reality, and that will be really, really exciting. Meanwhile, what's happened is it's given the computer science theorist a whole new model of computation to play with, and they're having a blast. I mean, they're doing great stuff with that. It's giving us, as scientists, it's giving us a much better sort of hands-on working level quantum mechanics, rather than this sort of pie in the sky, oh my God, what if I measured it sort of thing that hangs out. And there are problems, as I mentioned, and there are problems that have to be worked. We don't see anything that is in principle a complete showstopper, but the wave functions of electrons tend to get coupled to other stuff in the universe, and when they do that, they tend to lose their coupling with the ones you want, and instead couple with somebody that you don't want. And I guess if you're working in companies, you've probably seen the human equivalent of this going on. And so you can lose the information that way. And that's right now people's biggest concern about quantum computation. So in summary, I would say that digital systems, they look like the whole world to us today. I look at them as a start on a range of computing paradigms that will be with us 50 years from now. 50 years from now, I suspect that we won't be using computer and digital computer as the only words that describe computation, that we'll have other kinds of things that we recognize as computation, like the things that are done in the nervous system, the things that are done in quantum systems. We'll recognize those as doing interesting forms of information processing. That communication on the network won't be the only thing that's interesting. We'll actually be doing more interesting problems with the real world, with real time, with real perception, with real understanding of the world around us. We'll have many more ways to get inputs from the natural world into our cyberspace, and that's all going to be a very, very exciting 50 years.